Hello. So now we'll study the spectral distribution of energy. So when we plot the graph between E lambda and lambda, this kind of graph we get. One by one we'll study. What is E lambda? The E lambda is energy per unit second per unit wavelength. So let's discuss this more. So in case of radiation, when the radiation is happening, let's say this is our body and it is doing the radiation. So some Q naught will be going out, and or if you want to call it E, that's also okay because it's the emission. E stands for emission. So emission is going out, and when the emission is going out, we have a formula, Stephen's formula we are having. So emission of a body is equals to sigma A T to the power 4. So in case of radiation, this emission which is happening is a discrete process. This emission is not going in terms of wave, it is going in terms of pockets of energy. Meaning this emission is not a continuous process. This body is throwing the packets of photon h nu. And when this body is throwing the photons there, each and every photon is not having the same frequency or wavelength, they are having the different frequency and different wavelength. So this body is throwing the energy, and the rate of throwing the energy is equivalent to this. But when this body is throwing the energy, it is throwing in terms of photons. So it is like it is throwing n1 photons of hc upon lambda 1. That is throwing n1 photon per unit second for lambda 1 wavelength. It is throwing n2 photons of lambda 2 wavelength. It is throwing n3 photons of lambda 3, and it goes on till infinity. So see, it's not like this energy is going out from the body continuously. It is not going in case of a wave. It is going as a particles. So this body is continuously throwing lot of particles having different wavelength. So when over a period of time, when we collect those particles, and after collecting those particles over the period of time, if we collect those particles in containers, so this is a container in which lambda 1 wavelength we are putting, this is a container in which lambda 2 wavelength we are putting, in this lambda 3 and in this lambda 4 as an example we are putting. So over a period of time, let's say delta t time, we have placed n1 photons here, n1 photons. Here we placed n2 photons here. Here n3, here n4. There are photons. So we are having energy stored corresponding to these wavelengths. And these wavelengths will be very nearly closed. So this n1 is number of photons per unit second, n2 also number of photons per second. This is the rate basically. So when we have this, so we'll be having the energy corresponding to lambda 1 here. So this energy n1 times of hc upon lambda 1, this will be corresponding to lambda 1. This energy will be corresponding to lambda 2, and this energy will be corresponding to lambda 3. So this is energy corresponding to lambda 1, this energy is corresponding to lambda 2, this energy is corresponding to lambda 3, and it goes on. So this is nothing but spectral distribution of energy. You divide the energy based upon their particular wavelength. So this much energy is coming corresponding to lambda 1, corresponding to lambda 2, and it goes on. And when you place these energies, when you put these energies onto y-axis or upon x-axis, when you place the lambda, so basically what you do, corresponding to different lambdas, let's say I go for lambda 1, lambda is equals to lambda 1 here. So corresponding to lambda 1, I go to the graph, and this point, I go to the y-axis. This is the energy, this is the point, this is the level of energy this emission is having corresponding to lambda 1. So this is your E lambda 1. So we keep plotting these energies corresponding to different lambda 1, and we plot the graph. So this graph is spectral distribution of energy. Okay, so you can see here this total energy, when you collect all these energies, it is equivalent to that energy, sigma A T naught to the T to the power 4. It gives you that much value. Okay, any problem there? So as you can see here, these are the energies, and upon x-axis we are having wavelength, upon y-axis we are having E lambda. Okay, so this graph, this shape of the graph depends upon temperature, because these spectral energies depends upon this temperature. As you will be changing the temperature of the body, these energies in different lambda will get redistributed. Okay, so one more thing you can see here. If I do E lambda and if I integrate it with respect to D lambda, so ultimately we have divided these energies based upon the lambdas. And if I integrate this, E lambda, D lambda, E lambda is corresponding to these. This is E lambda 1, E lambda 2, E lambda 3, E lambda 4. So if I do E lambda, D lambda from 0 to infinity, if I consider all the wavelengths, so that will be equals to sigma A T to the power 4. That's a total energy emitting. Okay, and E lambda, D lambda, if you see, this is nothing but the area under the curve. This area, this total area under the curve, that is E lambda d lambda from 0 to infinity, and that value is equals to sigma A T to the power 4. So basically this area is proportional to temperature to the power 4. So if you increase the temperature, obviously this area will be increasing, and to increase the area, this curve will shift upward. Okay. So as you will be changing the temperature, this area will be shifting upward. As well as if you will be decreasing the temperature, this area will be coming down. So there is one thing in this spectral distribution, that is the area. And there is one more thing we concerned about, and that is this energy. If you see this energy, this is the maximum possible energy, and we call it lambda m. So in any curve corresponding to any temperature, you find one wavelength corresponding to which the energy is max. So basically out of all these boxes, there will be one box corresponding to which when you will calculate the total energy like that, that energy will have the maximum value among all. Okay. So if you are changing the temperature, one thing is total energy is going to change. If you change the temperature, the total energy in all the boxes is going to change. Now the second thing is, I want to know, when I'm changing the temperature, total energy is changing. What about that box which was having the maximum energy? Is that box is also changing? So how this energy in the individual boxes are redistributing, and there is a box which is having maximum energy, well, whether that energy will remain same or is it going to change upon changing the temperature. So upon changing the temperature, one thing is sure, this area is going to change. What will happen to this topmost point? We want to know that also. So what happens when we change the temperature, when we increase the temperature, the value of lambda m decreases. So basically this peak comes on the left side. This peak moves towards left when we increase the temperature, and when we decrease the temperature, this peak moves towards right. Okay. So upon increasing the temperature, graph is moving upward and the peak is moving leftward. Upon increasing the temperature, graph is moving up and peak is moving in this direction. So basically, can we say that this point is going in this direction? If you increase the temperature, upon increasing the temperature, this point is going to move in this direction, and if you decrease the temperature, this graph will be coming down, as well as this point will be moving rightward. So in total, the movement will be in this direction. This will be when you decrease the temperature. If you decrease the temperature, this movement will be happening in this direction. Okay. So if you combine both of these, the graph you will be getting at different temperature will be having that kind of shape. So this peak, if you see, this peak is shifting. This is lambda m1, this is lambda m2, and this is lambda m3. This is at T1 temperature, this is at T2 temperature, this is at T3 temperature. As the temperature is increasing, graph is moving up because the total energy will increase. So the area also increases. As the temperature is increasing, the wavelength corresponding to which you were getting the maximum energy, that is decreasing. So the graph is shifting on the left side. One more point you should memorize, or you should remember, for the same body, no two graphs at different temperature can intersect. Meaning any graph you are making, if these graphs are at different temperature, they can never intersect. So they will either go up or down. No two graphs can ever intersect at any point whatsoever possible. Okay. So the relationship between the delta m and the temperature, we write that relationship, and that relationship is equals to delta m multiplied with T is equals to B. This is your Wien's law. We'll discuss that in detail in the next lecture. So in this chapter, in this topic, we are learning spectral distribution of energy. So what we do, we divide this total energy corresponding to their wavelength. And that is what spectral distribution is. So corresponding to different wavelength, whatever is the energy, by collecting the photons and multiplying the energy of single photon, we plot these energies across the y-axis, and along x-axis we are plotting the wavelength. We get this kind of graph. In this kind of graph, if you can see, there is a point where the energy is max. There is a point corresponding to lambda for which the energy was maximum. That point, that lambda, is not the maximum wavelength. Maximum wavelength will be on this side. This is the wavelength corresponding to which we are getting the maximum energy. Okay. So we wanted to learn about this graph. What will happen with this graph when the temperature is going to change? So in this graph, there are two things. One is this peak and second is the area. Area of the graph represents the total energy whatsoever from 0 to infinite wavelength. So total energy is equivalent to this. So this value represents the total energy, which is the area under the graph. So area under the graph is proportional to T to the power 4. So if we will increase the area, if we will increase the temperature, obviously area is going to increase, this graph is going upward. Along with that, from the Wien's law, we have a relationship between temperature and lambda m. That relationship is this. So if the temperature will be increased, lambda m will decrease. So this point will move towards left. So the movement of this peak will be happening along this line. This is in between left and up when the temperature is increased. When the temperature is decreased, it will be happening along this line, which is in between down and right. Okay. So that's how the graph will move. No two graphs at different temperature for the same body can intersect. That's the law, sort of a thing. Okay. Thank you.